Hi everyone, I'm Madame Foufa from CA List in France, and I'm going to present you our work with prophecy on graph neural networks combining event stream and periodic aggregation for low latency event-based vision. Latency is critical in some vision applications, and our proposition is to use a full event-based approach as opposed to a frame-based approach. Why? Because in terms of data acquisition, event camera, they can generate events asynchronously at light intensity changes with only tens of microsecond latency per event, while RGB camera, they need to acquire frames synchronously with a typical frame rate of about tens of milliseconds. And then for the data processing, we argue for event graph because they really match event camera behavior, because computations can be triggered as events arrive, and we can output a prediction with only tens of microsecond latency per event. So that's what we're going to show here. While a frame-based neural network like a CNN, which computes frame by frame, will typically take about tens of milliseconds per frame. So in total, we show that with our approach, we can reduce the latency by 3 orders of magnitude. But the challenge is to achieve this ultra-low latency event prediction. The event graph operation must satisfy one constraint: no information from the future can be used. Why? Because the only information available at present time is the information from the past. The information from the future is not yet available, and we should wait to get it, and so it will necessarily impact the latency. The problem is that it limits the field of view of graph operations. It means we cannot do any aggregation, any pooling. And so our goal is how to integrate enough context information in event graphs while not adding any latency. To solve this challenge, we propose a two-branch architecture with event branch and a periodic branch. The event branch, the goal is to be fully event-based with no accumulation, so that once we get an event, we can directly compute all its related graph operation and compute its optical flow prediction, here in the case of an optical flow application. And it will just take information from the periodic aggregator without waiting. I will explain now how. The periodic branch aggregates event data to inject context in the event head, and its goal is to improve the accuracy because it can aggregate information while not adding any latency. And how is this possible? The trick is that the information that the events received in the merge will be features that has been computed on past events, actually 2 frames backward, to not induce any latency overhead. Why? Because it takes 2 frames for the periodic aggregator to first accumulate events and then compute their features. So this is the only information we can get with 0 latency. So is this architecture more accurate, and especially at low latency? Because in the end, if we have a solution that can predict at lower latency but is not more accurate, it's useless. And so that is why we study the evolution of the error with time of the 2 outputs of our network. The periodic one that is delayed, so has no access to the most recent information because it is 2 frames delayed, and the event one, which has access to both the periodic one and the most recent events in the event branch. And we can see that yes, indeed. So here is a very challenging data set where there is very drastic optical flow changes from one timestamp to the other. And we see that at the moment of a change, both errors rise a lot, but then the periodic prediction, the error stays high for a long time, actually corresponding to the 2 frames delay, because it does not have access yet to the information of the motion change, while the event branch can leverage the most recent events to recover the accuracy faster. So overall, the periodic branch improves the overall accuracy, but the event branch improves the latency of detection of optical flow changes. We wanted to show that our results are not dependent on the periodic aggregator architecture, but actually are inherent to any frame-based method. So we did the same experiment with the state-of-the-art CNN method, so there is absolutely no graph in it. And we observe the same phenomenon because it is inherent to a frame-based processing, which means that in real time, the only available information is the predictions 2 frames backwards. And so if there is a motion change happening in between, it cannot detect it before 2 frames later. So we really see the benefit of our approach combining even graph with periodic aggregations. In terms of hardware latency, we measured the processing latency of our method versus the state-of-the-art CNN. It is lower in a GPU, but we argue that our method could be most beneficial on a dedicated implementation such as FPGA, where the latency is estimated to be about 50 microseconds. Thank you for your attention.